our second talk is open source sequence development in myocardial T1 mapping by Gaspar. She completed her master's degree in biophysics and biomedical engineering at the University of Lisbon in 2015. In 2022, she completed her PhD in biomedical engineering in Instituto Superior Técnico under the supervision of Rita Newell. Her work focuses on open source techniques and both acquisition and reconstruction method in quantitative MR, including the implementation of SMS methods with the aim of improving accuracy and spatial resolution of T1 mapping techniques. Okay.
Yes,
First.
thank you very much for the introduction. Following Nicola's presentation about studying different methods and different ways of doing open source sequences for T1 mapping, in our group, we developed a method for doing myocardial T1 mapping in an open source way. So the idea here is that T1 mapping in the myocardial, like the other ones, allow to have a quantitative measurement of the tissue, characterization, and it allows to identify diffuse fibrosis and other changes in the tissue in different myocardiomyopathies. So the idea here is that we have this objective measurement, but like Nicola said, this can change from scanner to scanner, between vendors, if the sequence is not exactly the same. So, on top of that, these methods for myocardial T1 mapping, the method used in the clinic, which is the modified lock-locker inversion recovery, usually is performed with only 3 short axes, which corresponds to a short coverage of the tissue that we want to measure. And each one of those axes are obtained in the different breath holds, which can take a lot of time, especially when the patient has to recover between slices. In addition, it has a limited resolution, which can lead to partial volume effects, for example, in the presence of fat, and also motion-related artifacts. So, if we want to improve this, the conventional way is to have the vendor-specific environment that we have access, and then change the sequence in that environment. However, this is really difficult to access. Not only that, also the learning curve is very steep. So we use the open source framework, one that Nicola has also mentioned, which was PulseSec, and develop an open source myocardial T1 mapping, OpenMoly. With OpenMoly, the idea is to have a similar sequence to the modified lock-locker inversion recovery sequence with 2 inversions and 8 times of inversions. This sequence is available in our repository, both in Python and in MATLAB, to create the file to run in the scanner. So if you want to play with it, if you want to test it, you are very welcome. In terms of testing of the sequence, we tested both in a phantom and also in 21 healthy volunteers in a 1.5 Tesla scanner. For the reconstruction, we use phase-sensitive inversion recovery, and also we used in-plane undersampling. So we also did, within the same session for both the phantom and the volunteers, we did a test-retest. So within the same session, we repeated each sequence 2 times. Starting with the phantom, so in here what we tested was OpenMoly and Moly with a linear and centric k-space filling. And what we can see here is that with for the vials that corresponds to T1 of reference that are lower, the attainable the time of inversion was a little bit longer for the linear case, because in this case was fully sampled, so it was not able to completely estimate the T1 values. However, if we look to the vial that, at least for the T1, is more it's near the value that is present in the heart, we can see that all the methods are very similar. In terms of repeatability, they are also very similar between them, between Molly, Open Molly, with only here a slight outlier for the Molly case, but we think this is related with the fact that corresponds to this vial or this 4 vials, and we think that the Molly, the clinical method, is optimized for the other values, so with this, it was not able to correctly estimate. In terms of the maps that we obtained, we can see in the first line Molly, in the second line Open Molly. Open Molly presented here a little bit more noise than the first one, the Molly, the clinical method. However, we think this is related with the type of reconstruction we did, because with Molly we got partial Fourier acquisition, while with our Open Molly we were able to acquire the whole case space. So this introduces some blur, but if we do, we exclude that part of the acquisition here for both sequences, they are very similar between them. For the segmental distribution, they are also similar, although for the apex, there are an overestimation for Open Molly. We think this is related with different breath hold positions that can lead to more errors, and in this case, it led to an overestimation that is also visible here in terms of the precision. For the differences between them, they were not statistically significant, and although we can see here a trend where higher values present a higher difference, but this may be related with the fact that we have this bias of the apex. So for the repeatability, these are really good results as well, because the repeatability was really similar between for Molly and Open Molly, and this coefficient of repeatability coefficient is also similar to the one that we see in the literature, and these are really good results in terms of repeatability. So for this part, which corresponds to the base sequence, the Open Molly sequence, we got values that were similar to the Molly methods, with values that are similar to the ones present in the literature, although we have a slight decrease in precision. The repeatability presents also similar, and in terms of the fact that it is open source, which can be a groundwork to build different implementations and different improvements. Currently, we are studying intra and inter-center reproducibility, special at 3 Tesla, and we will be participating in the reproducibility challenge. So if you want to join us and test the sequence, you are very welcome. Now we have this awesome sequence that is the base myocardial T1 mapping, but it still has the limitations that I mentioned before. So the idea here is we have this sequence and we will build on top of that, and that's what we did. So what we did was to try and acquire all the slices at the same time, the 3 slices that I mentioned in the beginning, in order to have all the sequence in only one breath hold. And for that, we use simultaneous multi-slice. And for that, so this new sequence is the Open Molly SMS, where a fully open source sequence as well, which was developed in the same PulseSec framework, presents an auto-calibration structure for a fast self-contained T1 mapping sequence. So with only this sequence, we have all the call information that we need, and we can also reconstruct all the slices. And likewise, is also available at our repository if you want to test it, if you want to know how it works. And specifically how we implemented this. We implemented this combining 3 different methods. First, the verse multiband pulse, which allow us to have TR, the shorter TR possible, which in the balanced steady state precession sequences are very important because the shorter TR, the wider the pass bands and less artifacts we will have. And with this implementation, we were able to decrease the time of the excitation pulse without many side lobes. That's with this implementation. Then we use a blip balanced steady state precession, which allow us to shift one slice related to the other and make it easier to unfold the slices afterwards. So by doing this in the gradients, by introducing gradients in the slice direction instead of doing it in the RF pulse, we are able to have to maintain the artifacts in the same position and don't change the pass bands that I mentioned. So in here we have at the left the implementation where we don't have this split and the slices are overimposed in the FOV, and in the right one we can see here that they are shifted one related to the other, making it easier and with less noise amplification. Finally, I will not go into much detail explaining everything, but the idea here is that we have auto calibration blip pattern at the last image, so it doesn't disturb the next one. So it was our approach, and with this we ensure that the coil information that we have is exactly in the same position as the rest of the acquisition, and with that we can avoid some mismatch between one and the other that could lead to artifacts. And we tested two types of calibration, one with a balanced steady state precession and another one with a spoil gradient echo. In terms of testing, we did also in a phantom and in 5 healthy volunteers. In this case, we test Molly, open Molly with SMS2, where two slices are excited at the same time, and open Molly with SMS3, where three slices were excited. And in this case, starting with the Phantom, so the Phantom was the same, ISM Remnist Phantom, and in this case, we image three levels of the Phantom. And if we focus on the T1 array, which is corresponds to the slice number 2 in this case, we can see that they are very similar, although here when we don't include in plane acceleration, this can be a little bit tricky because the acquisition is longer. But in vivo, this would not be the one that we will be using. Instead, we'll be using the ones with in plane acceleration. Now again, if we concentrate on the values that are more that are near the ones present in the in vivo, which corresponds to the red ones in here, we can see that they are very similar, and especially vial number 3, which is this one, it's also very similar. Although for SMS3, which corresponds to the 3 slices being excited at the same time, that's already a little bit increase here in the standard deviation for both auto calibrations that we tested. In terms of in vivo acquisition, there is here the first line is the Molly, second one open Molly, and the last two corresponds to the open Molly SMS2. And we can see that they are very similar between them in this case. In terms of precision, it is a little bit worse, but this is expected due to noise amplification. But in terms of values, they are very similar and not statistically significant, especially between open Molly and open Molly SMS. Then, if we look into the SMS tree, where the three slices are required, we can also we can see the expected noise amplification in this case, where we can see when comparing with the open Molly case. And if we look here, in terms of the dispersion that we see is also a little bit wider, but in terms of mean values, they are very similar. And in here, we can also see that the difference between the acquisition with the auto calibration with balanced steady state preprocession and spoil gradient echo are not that different between them. So in terms of the summary of this work. So if we use open moly or moly, we'll need 3 bed holes to acquire three slices, and this can go up to 4 minutes depending on the time that a patient needs to recover between breath holds. If we acquire the SMS2 open moly, we'll have only 2 breath holds, and with that 2 breath holds, we can acquire 4 slices and still have a robust response from the methods. And finally, we can also use only 1 breath hold and have all the slices at the same time, in this case with a slight increase of noise amplification, but we think this is also could be overcome with a better set of coils, that we were a little bit limited in our center, but we think that this could also be improved with a different framework in that context. In conclusion, with this sequence, we don't need any additional calibration scans, which can avoid these motion errors between a mismatch, position mismatch between them. The results are similar to moly, especially for open moly SMS2. This self-calibration strategy can also be used in different balanced steady state preprocession based methods, as for example, cine acquisitions, and would allow a faster, more comfortable scan that is available in different centers to test. And in the future, we want also to test that in different centers, and in a 3 Tesla scan that we are also trying to install PulseSec. And if you want to play with this, it's also available in our repository. All the steps that I show here, they are freely available. If they are not in our repository, they are in another one that is also available to download. So this is also very accessible. So with this, I want to thank you all for listening, and also my colleagues and my co-authors to help me out with this. Thank you very much.